All right. So today we're still dealing with exponential functions, but now we're looking at a specific subtype of function. By the way, if you guys want to turn the light off, go ahead and hit it off. So today we're dealing with the subtype of exponential functions called exponential growth and decay. Now, these types of functions are set up pretty much the exact same way that all the exponential functions we've been doing previously are set up, but they are used specifically for more in context problems. So you'll see these mainly with word problems. And to be honest, these formulas are the ones that are very real world applicative. All right. So you can really apply these in the real world. Most of the time, you'll see these in problems dealing with population and money. All right. So, as always, we start with our I can statement. So, for this lesson, it's I can write an exponential growth or decay equation given a word problem. I can also identify the percentage of increase and decrease based on the equation. All right. So it's technically two new formulas, but setup wise, it's pretty much the same as y equals a times b raised to the x power, which we've been doing for the past 2 days. All right. So these two formulas that we're going to be looking at are the exponential growth formula, which is this first one, and the exponential decay formula, which is the one underneath it. And they are seriously almost the exact same formula. There's just one sign difference. So the growth formula is f of t is equal to a times 1 plus r raised to the t power. And decay is f of t equals a times 1 minus r raised to the t power. So literally, when it comes to these, they're pretty much the exact same formula, except growth has a plus and decay has a minus. That's the only difference between the two. All right. Now, it has some new values that we're putting into those formulas that you may not be affiliated with. So we're going to talk about what each one of those letters stands for in terms of the problems that you'll see. So first off, letter A. Letter A in growth and decay formulas are pretty much the same as letter A in just any exponential formula. So when we were talking about exponential functions in general, what did the A typically represent? The y-intercept. All right. Same thing here. If you were looking at an exponential growth or decay graph, the A value would still be the y-intercept. However, in terms of the problem, your A value is going to be your initial value. So your initial value or the value that you started with. So how much money you put in the bank account originally, what your population was originally before any time has passed. That's what your A value in context will be used as. It's your initial value. Now, your T replaces the X in this case. And I want you to think about this carefully. what do we use the variable t typically for? To represent time. And that's exactly what t stands for in this case. It represents time. And remember, it replaces your x value in terms of the original generalized function. But t will be any form or unit of time. So seconds, minutes, hours, days, weeks, months, years, whatever. All right. It's any form of time. Now, the last one, R, means the rate. So R in this case will mean your rate of growth or decay. Now, in the word problem themselves, this value will be given to you as a percent. But when you put it into your problem, so when you plug the R value into the problem, you have to convert that percent to a decimal. So in the problem, they're going to give it to you as a percent. So that's the percent that you're growing. But when you put it into the formula to set up the equation, you have to convert that percent to a decimal. Now, does anyone remember how to convert a percent to a decimal? So think about it. What's the highest percent that you can have typically? 100. So to convert to a decimal, it's almost like making a fraction. You take whatever percent that you have. So like for instance, say 10%, divide it by 100, that's your decimal. So 10% is equal to 0.1. And you can just put that in your calculator. So very simple conversion. You just divide it by 100. So if you're going from decimal to percent, you multiply it by 100. Very, very simple conversion. Now, let's look at some other features of exponential growth and decay graphs. So, an exponential growth graph. This is an example of an exponential growth graph. What type of exponential graph does this look like that we've already seen before? It's positive, or in other words, it's increasing. So this is an increasing graph. So in order for it to be an increasing graph, what do we have to have? So if we're looking at any exponential function, how can we tell right off the bat that's going to be an increasing graph without graphing it? What number? The b value is greater than 1. So the b value is greater than 1 in our original equation. Now, the actual formula for exponential growth is f of t, and I'm just restating what's up top. F of t is equal to a times 1 plus r raised to the t power. Even though it does not flat out state b in that formula, we do have a b value. Where do you think my b value is in that formula? Not just the r, the 1 plus r. So notice how this is a placeholder for the b in our original. So y equals a times b raised to the x power. The 1 plus r is the placeholder for the b value. So this 1 plus r has to be your b value. Now, let's talk about if the 1 plus r actually gives us a number greater than 1. So think about it. Your r value is usually written as a percent or as a decimal. So if you add 1 to a percentage decimal, so in other words, it's definitely going to be less than, the decimal itself is going to be less than 1. You add 1 to a decimal, will that give you a number greater than 1? So for example, if I had 90% as my R value, that converts to 0.9. I add 0.9 to 1. Does that give me a value greater than 1? Yes. So if you're adding 1 to your rate, you're always going to have a number greater than 1. So if they ever ask for, so your B value in this case, you'll see it called your growth or decay factor. And so if you get asked that, all you got to do is do 1 plus R. So whatever the rate is plus 1. And that would be your B value. Now, on the opposite side, you have exponential decay. Very, very similar. So if we're looking at a graph for exponential decay, what type of exponential graph is this? It's a decreasing graph. And what has to happen with a decreasing graph so that we know it's decreasing? Nope. What? Right. The B value has to be in between 0 and 1. So in other words, the B value is a what? A fraction. So the B value is a fraction. Now, the formula that we deal with for exponential decay, just to restate it again, is f of t is equal to a times 1 minus r raised to the power of t. So again, if we have y equals a times b of x, what's replacing my b value in the formula for exponential decay? So what would give me my b value for exponential decay in the formula? I heard someone say it. It'd be what? So guys, what was it for exponential growth that gave us the b value? 1 plus r. So on the flip side, exponential decay, the b value would be equal to 1 minus r. So 1 minus r, that gives me my b value. Now let's think about this logically if that fits for an exponential decay graph or decreasing graph. If you have a decimal, which is taken from a percent, so that decimal is smaller than 1, and you subtract it from 1. So let's go back to the 90% example. Convert that to a decimal, 0.9. 1 minus 0.9. Will that give me a number that's less than 1 and between 0 and 1? So will that give me a number between 0 and 1? If I do 1 minus 0.9? Yes. And it does technically give me a fraction. But in this case, we'll keep it as a decimal. So in this case, we'll keep it as a decimal, but it still has to be between 0 and 1, that decimal. So it does always work. And again, that means, just to restate, your B value is also known in this case as your decay factor, which again, you would just use the formula 1 minus r to get. All right. Now, let's do some examples. So let's look at, inside your packet, let's look at this first example. So we're going to find the multiplier for each rate of exponential growth or decay. So in other words, we're finding the exponential growth or decay factor, all right, for each of these. Now, the method you use for this is that you start at 1. Now, what is 1 the same thing as a percent? So 1 is equal to what as a percent? 100. So again, 100%. That's what that 1 represents. We're subtracting it from 100%. Then we add the growth. So if it's growth, we're adding that rate. If it's decay, we're subtracting that rate. And we would divide the result by 100 to turn the rate into a decimal. So I kind of do things backwards. I usually turn my rate into a decimal first, then just add or subtract it from 1, depending on what it is. All right, so we're going to practice that. So all we're doing for these is we're finding that B value that we would put into our hypothetical equation. All right. So for the first one, I'm saying we have a 12% growth rate. So, is this going to be an exponential growth or decay problem? Growth, obviously, it says growth. So what formula for B value will I use? So for finding the B value, what formula? 1 plus R. So I'm using 1 plus R for this one. And what's my R value in this case? Just leave it as percent for right now. What's the R value? 12. So the R comes from 12%, but I'm going to convert it to a decimal by dividing 12 by 100. And again, you can put that in your calculator real quick. But if you do that, you should get 0.12. Now I'm going to place that R value back into my formula. So this is going to be 1 plus 0.12. And again, you can put that in your calculator, or honestly, that's a very simple calculation. You would get 1.12. So this would be your growth factor or your B value in your equation. Now let me ask you this. What's that as a percent? What's 1.12 as a percent? So think about it. What's 1 as a percent? 100. What's 0.12 as a percent? Right, so 1.112 will be 112. So this is the same thing as 112%. So the reason that this implies an exponential growth, what's happening is, if we put it into context of a real situation, let's say that I put $1,000 in the bank and it grows at an interest rate of 12%, which that's a very, very high interest rate, by the way. That never happens, but just hypothetically. All right. That means that they're going to take, the way the bank will calculate this is that they're going to take 12%. They're going to figure out what 12% of my initial is, so 12% of 1,000. And then they're going to add it back to 100% of my initial, which is the 1,000. So that's where we get 112 from. They're taking my initial and adding on another 12%. So the new value will be 112% of the original. All right. So that's what it's talking about. We're growing by 12%. So in reality, our new value will be 112% of the original value. Now, on the opposite side, we have decay. So 7% decay. So obviously, this is exponential decay. And what formula do I use to find my decay factor or your B value? 1 minus R. So same process, essentially. Your 7% is your R value, which you convert to a decimal. So you do 7 divided by 100. So that should give you 0.07. All right. Then you plug that in for R in the formula. So you have 1 minus 0.07. And again, you can put that in your calculator and you should get 0.93. So that is your decay factor. Now, what's 9.93 as a percent? 93%. So when we're talking about decay, let's talk about cars. So let's say I bought a new car for 15 grand, which again, that's a very cheap car. So for $15,000, I bought a brand new car. As most of you may know, as soon as that car leaves the lot, it starts losing value. So if I try to sell that car the very next day, I would sell it for less than what I paid for it. All right. So it decreases at a rate of 7%, which that's about normal for a car. So it decreases at a rate of 7%. So that means what they do is they take that 15 grand and they figure out what 7% of that 15 grand is and then subtract it from the 15 grand. So in reality, all they're doing is figuring out what 93% of 15 grand is, and that's how much money the car's worth at that point in time. So that's what it means by a decay. Does that kind of make more sense? The difference between exponential growth and decay? So growth, you're making more. Decay, you're making less. All right, try those other two on your own. So even though they're decimal percentages, same process. Take a minute, try those two on your own. So these are very quick. All right. Then I only want you to give me the decimal. You don't have to convert it back to a percent. You can if you want to, but I really only want the B value or the number in the decimal. All right, thumbs up if you're ready. All right, so check your answers. So for 4.5% growth, I got 1.045. For 8.4% decay, I got 0.916. Is that what y'all got? Yes, no, maybe? Does anyone need me to explain them? Yes, ma'am.
I got 0.04.
You have to add the 1 to it. All right. So now what we're going to do is we're going to work backwards. So originally they gave us what our percent growth or decay is. Now they gave us the function and they want us to use the growth or decay factor or the B value, hint, hint, wink, wink, to figure out the percent of growth or decay. So we're working backwards from where we started. So let's look at letter A. First off, is this going to be an exponential growth or decay? And how do you know? So letter A, is this going to be an exponential growth or decay? So remember the glaringly obvious thing that we talked about that definitely tells you it's a growth or decay problem. It has to deal with your B value. It's a growth. Why is it a growth? Because our B value is greater than 1. So my B value right here is greater than 1. So this has to be a growth problem. So we're only messing with the B value. We're going backwards from the B value. So this is 1 plus R. Now, we got to kind of work backwards. So 1.05 is what we get after we do 1 plus r. So what do you think a good strategy would be to find my r value? How do you think I could find my r value? So think about it. If 1 plus r is 1.05, how can I find my r value? Subtract what? From? Nope. So if 1 plus r is equal to 1.05, what's the easiest way I can get my r value? Subtract 1 from 1.05. So this is the exact same thing as 1.5 minus 1 is equal to r. So in other words, my r value would be equal to what if I subtract 1 from 0.5? So 0.05. Now, they wanted this as a percent. So how do I convert a decimal to a percent? I only do what? It'd be 5%. So you just multiply this by 100, and that will give you the percent. So this would be a 5% growth. Make sure you state whether it's a growth or decay. So it's a 5% growth. All right. What about letter B? First off, is that equation a growth or decay? Decay, how do you know? The b value is lower than 1 and it's also greater than 0. So it'll be a fraction of some sort. All right. So we're dealing with a decay. So again, since we're only messing around with the b value at this moment, that means we're just dealing with 1 minus r. So we're saying that 1 minus r would equal 0.85. So what would be the most simple way to figure out what my r value is? Not necessarily add 1. Nope. So it has to deal with subtraction. But what from what? So think about it. If 1 minus a number is equal to 0.85, that is the same as saying 1 minus what is equal to r? So 1 minus r is equal to 0.85. That also means that 0.85 plus r is equal to 1. You guys see it now? So how do I find what my r is? So what can I do to get r? Switch it. So 1 from 0.85. So you subtract 0.85 from 1. So you do 1 minus 0.85, and that gives you r. So essentially, you just switch the places of these two to get your r value. Now, if I subtract those two, what would my r equal? (0.15). And again, as a percent, because we want it as a percent, you'd multiply 0.15 by 100, and you should get what? 15% decay. Don't forget to write decay after it. Any questions on how to find your percent rate? All right, try C and D on your own. Hey, if you need to shut the door because it's loud outside, you can. All right, it's very quick calculation. Shouldn't take you too long to get those two. All right, thumbs up if you're ready. Give you one more minute. All right, check your answers. So I got 4.5% growth for C and 23.5% decay for D. Does anyone need me to go over either one of those? How'd you guys do? Do pretty well?
Yeah, I did good. I didn't finish the second one.
All right. So now the next thing we're going to do is actually look at some actual exponential growth and decay word problems. So we're basically going to take the skills that we just did from the previous two and put them in terms of the word problems. So let's look at number one, or word problem number one. So the number of bacteria in a lab experiment is increasing by 2.5% per minute. The experiment started with 200 bacteria. So it first wants us to know what the growth or decay, not rate, this is factor. Growth or decay factor is. So essentially what we were doing at the very beginning of examples. All right. So what we were doing was said 12% growth, 7% decay. How do I find it? First off, is this going to be a exponential growth or exponential decay problem? And how do you know? Right. This word right here, increasing, implies that we are growing. So this has to be an exponential growth problem. Meaning that we're going to be dealing with the formula f of t is equal to a times 1 plus r raised to the t power. So specifically to find the growth factor, we're using the b value, or the 1 plus r. So how can I set this up to find it? What's my r value here? 2.5%. So this is my r value. So first things first, I need to convert it to a decimal. So if I do 2.5 divided by 100, that should give you 0.025 if you put that in your calculator. Then what do I do? So that's my percent as a decimal, and I want my growth factor. So I then have to do what with that decimal? Well, we just converted from a decimal to a percent. Or we just converted it from a percent to decimal, so we'd end up with what we started with. So guys, look at where it said on the previous examples, look at where it said 12% growth, 7% decay. Once I got here, what did I do next? So I converted my rate to a decimal first. Then I did what? I heard it. Who said it? So you do the 1 plus r, replacing the r with that decimal. So we're going to do 1 plus our r value, which is 0.025. And if we equal that, this will be 1.025. So this is our growth factor. And it's important because that's going to help us with the next question, which is to write an exponential function that models the number of bacteria Y as a function of the time in minutes that has been growing, which is represented by X. So again, we're using this formula to figure all that out. All right. So first off, we already got our B value, or what's going in place of the 1 plus R. But we still need to figure out what our A value is. What did I say your A value represents in terms of exponential growth and decay problems? It always represents what? Well, not necessarily the y-intercept. In terms of the problem, what would it represent? So guys, look at the front of your cover. What did I say the A value always represents? The initial value, or my starting value. What's my starting value? How much bacteria did I start with? 200. I started with 200 bacteria. So that 200 is my A value. So I'm going to have Y equals 200 times, what do I put in place of the 1 plus R? The growth factor that we got from part A, so 1.025. And then T, instead of writing T, we're going to write X, because it said to replace the T with X. And that's all you got to do. So the hardest part is getting that growth or decay factor. After that, you just need to figure out what you started, how much you started with, and then just put it in the correct spots of the formula. Now, it then asks how many bacteria to the nearest whole number does your model predict will be present after 1 hour of growth? So 1 hour of growth. If we're talking about an hour, are we referring to our X value or our Y value in our equation? The X. So we're referring to X here. Now let me ask you this. Is X equal to 1 in this case? Are you sure?
No.
No. Why? Look at the units it started with. So look at part B. What did it ask us to write our X value in terms of?
Oh,
Mm-mm.
oh,
What time units did we initially write our X value in? Minutes. So we initially wrote our X value in terms of minutes. But then it asked us to find after 1 hour. If we write, so X in this case equals 60 minutes, because there's 60 minutes in an hour. So if you write a equation in terms of 1 unit, if they give you a different unit in another part of the problem, you need to convert to the original unit. So in other words, since they gave us hours, but we wrote our equation in terms of minutes, before we can plug our X value back into our equation to evaluate, we got to convert the 1 hour to minutes. You got to keep the units consistent. All right. So X is not equal to 1 in this case. X is equal to 60, which we're then going to plug in for X into our equation we got up top. So I would have Y is equal to 200 times 1.025 raised to the 60th power. And then from there, you can just put all of this into your calculator. So put it in your calculator exactly as you see it, and then round it to the nearest whole number so you won't have a decimal anymore. So take a minute, put that in your calculator, and tell me what you get.
880.
Did everyone else get 880? I'll give you guys another minute to put it in. Right, so you would get 880 what? Bacteria. Remember to write your units that your answer is in. So after 1 hour or 60 minutes, at the rate of growth that we had, we'll have 880 bacteria. All right. Any questions on this problem? Yes. When Chris gets back. All right, last problem. So you just bought a new car for $48,000. Your car depreciates in value by 8.5% annually. And first off, it wants us to find the growth or decay, not rate, factor. So it wants us to find the growth or decay factor. So first off, we need to determine, is this going to be an exponential growth or an exponential decay problem? And how do you know? Right. So the word depreciates means it's going down in value. So this is a decay problem. Now, if it said appreciates, that would be a growth. That means it's gaining money. All right. So that means that the formula that we're using is f of t is equal to a times 1 minus r raised to the t power. So what's my r value in this case? Because we're trying to find our growth factor. Or decay factor, sorry. 8.5 is my r value. Oops. So this is my r value. So I'm going to convert that to a decimal first. So 8.5 divided by 100. You can put that in your calculator real quick. You should get 0.085. What do I do next? So we're finding our decay factor. So similar to the example that said 7% decay. What do we do next? So we're essentially finding our B value, guys. So what do I do next once I get my R value as a decimal? Guys, what did we do in the previous examples where it said 7% growth? Right. 1 minus the 0.085. So we're going to do 1 minus 0.085. And what would you get if you put that in your calculator? Be what? 0.915. Or 0.915, I should say. So this would be our decay factor or our B value. So this would be our B value. And again, that will help us in the next part, which is to write an exponential function that models the value of the car as y as a function of the time in years x. So first off, again, we're still using this formula. All right. So we already know what our B value is, or the 1 minus R value. We already got that. What's my A value here? Where did I start at? $48,000. So 48,000 is my A value. So I would have Y equals 48,000 times what? What goes in those parentheses? Right, 0.915, or the value we got from the previous question. And it's all going to be raised to the x power. So that would be my equation. Then the last part is they just want us to apply it like we've been doing. So it wants to know what the value of your car is after 6 years. So 6 years, will that be an x value or a y value in terms of the problem? It's x. It's talking about time. And do we have to do any weird conversions or anything? Nope. Our units are consistent. We wrote our equation originally in years. They gave us a number in years. So x in this case is equal to 6. So I'm going to take that 6, plug it back in for x into my equation, and evaluate it. So, oops. y equals 48,000 times 0.915 raised to the 6th power. And again, you can put that all in your calculator. Now, it didn't tell us what to round by, but since our original is in dollars, let's round to the nearest dollar. So you shouldn't have any cents. So once you get your answer, someone raise their hand and tell me what you got. So put that in your calculator exactly as you see it. And once you get an answer, someone raise their hand, tell me what you got, and round your answer to the nearest dollar. So you shouldn't have any cents left over. Someone besides Foster, who's kind of been carrying y'all today. Elise.
28,168.8.
Right. So if you round to the nearest dollar, so get rid of the decimal, what would that be? So it's 20. So your y is equal to 28,000. What was it? 180 something? 160. Right. 169 because you got to round up because we went to the nearest dollar. And make sure you put that dollar sign to show your units. Now, let me ask you this. Does that answer make sense in terms of the problem? Is that like a reasonable answer that we can get? Yeah. Because if you think about it, if we're depreciating in value, yes, ma'am. All right. So I'm just going to quickly plug it in. So 48,000 times 0.915 raised to 6. All right. So we're just rounding up. So we're using the decimal place here to round up so that we get rid of the decimal place. So we're essentially using the 7 to round the 8. That's all it was. It was just a rounding thing. So when I say to the nearest dollars, remember, like, if you did it in terms of your dollar values, you could still have 2 decimal places after because that's how many decimal places you typically have with cents. But since I went to the nearest dollar and I don't want any cents, we would just get rid of the decimal place by rounding up. So like I was saying, this makes sense because if we're depreciating in value over the years, we should get a number smaller than what we started with. So if you put it in your calculator and you got a number bigger than 48,000, you most likely did something wrong. All right. So like from the previous problem, since we were growing in that problem, we should have gotten a number bigger than 200. If you had a number smaller than 200, you probably did something wrong. All right. So that's kind of a good way to check yourself. Ask yourself, does this answer make sense in terms of the problem? All right. Any questions on any of this? All right. So